All right, today we're diving into a puzzle that has obsessed some of the greatest minds in history for millennia. It's a problem so famously difficult that its name literally means trying to do the impossible. We are talking about squaring the circle.
So what's the big deal? Well, the question itself sounds pretty simple, doesn't it? How do you build a perfect square that has the exact same area as a given circle? And I mean exact, not close, not good enough, but precisely the same, down to the last infinitesimal bit. That's the heart of the puzzle.
And believe me, people were obsessed. For over 2,000 years, this puzzle captivated everyone. We're talking about thinkers from ancient Greece all the way to modern mathematical geniuses. This wasn't just some casual brain teaser, it was a genuine quest. You could almost call it the final frontier of classical geometry.
Now, to really get why this was so hard, you've got to understand the rules of the game. The ancient Greeks were very specific about this. You get two tools, that's it. A compass, for drawing circles and arcs, and a straight edge. Think of it like a ruler but with no markings. So no measuring, that's the catch. You can only draw circles and straight lines. Those are your only moves.
So this impossible ancient puzzle, why did it become such a big deal? Well, it really all boils down to what the Greeks were able to do.
You see, the Greeks were absolute wizards with this stuff. They could take pretty much any shape with straight sides, a triangle, a pentagon, you name it, and using just their compass and straight edge, they could whip up a square with the exact same area. It was like magic. So, of course, the circle, this perfect, elegant, curved shape, that was the next logical step. It was basically the final boss of geometry.
And so began centuries of getting closer. For the next 2 millennia, mathematicians threw everything they had at this problem. They never quite cracked it, but they got so close. And they quickly figured out that the key to the entire puzzle, the secret ingredient, was the number we all know and love, pi.
See, to square a circle, you have to be able to construct a length that's based on pi. So really, the story of this puzzle is the story of humanity's long, slow quest to pin down pi. It was this incredible march of progress. You had the Babylonians way back around 2000 BCE getting a decent approximation of 3.125. Then Archimedes came along and cleverly trapped pi between two numbers. And by the 5th century, the amazing Zhu Chongzhi had it nailed down to 6 decimal places. With every century they were zeroing in, getting more and more accurate.
But here's the twist. All of this incredible progress, all this getting closer and closer, it was all leading to a final answer that absolutely no one saw coming. In fact, it was the one answer nobody wanted.
And then, just like that, in 1882, after more than 2,000 years of trying, the case was closed. The chase was over.
The final answer? It's impossible. It just can't be done. That's it. This puzzle that had stumped the world's greatest minds for ages was officially unsolvable. So, why? Why is it impossible? Well, the reason is actually kind of beautiful, and it all has to do with just how strange the number pi really is.
Okay, so let's get into the nitty-gritty. The key thing to understand is that pi isn't just your standard irrational number. The kind with endless decimals that never repeat. It's something far weirder, a special class of number called transcendental. What does that mean? Well, to put it simply, it means you can't generate pi using basic algebra. It can never be the solution to a standard polynomial equation with rational numbers. It sort of transcends algebra. It exists on a whole other level.
And this is where it all clicks into place with those old Greek rules. See, it turns out that every single length you could possibly build with just a compass and a straight edge, well, they all correspond to what are called algebraic numbers. But since pi is transcendental, it lives in a completely different mathematical universe, a universe your compass and straight edge can never reach. It's like trying to fly to the moon using only a bicycle. The tools just aren't built for that world.
And the guy who finally proved this, who shut the door on this 2,000-year-old quest, was a German mathematician named Ferdinand von Lindemann. In 1882, he proved once and for all that pi is a transcendental number. And thanks to a powerful idea called the Lindemann-Weierstrass theorem, that automatically meant that squaring the circle was impossible. End of story. Case closed.
But wait, the story doesn't just end there. This is where things get really cool. Okay, so an exact solution is impossible. What now? Well, people got creative. The goal wasn't about finding a perfect solution anymore. It shifted to something else, crafting the most beautiful, the most ingenious approximations imaginable. And just look at some of these attempts. They are just brilliant.
Back in 1685, a guy named Adam Kochański came up with a construction that was accurate to 4 decimal places, which is pretty amazing. But then, fast forward to 1914, and the legendary Srinivasa Ramanujan creates this mind-bendingly elegant method that gets you an accuracy of 8 decimal places. 8! Just with a compass and straightedge.
And that's the real point here. These weren't solutions. These mathematicians knew it was impossible. No, these were masterpieces of geometric art. They were a celebration of human ingenuity, showing just how much beauty you could create within those strict ancient rules. They're like little geometric ballets.
And guess what? The story still doesn't end there. Even after it was proven impossible, the problem continued to fascinate people. Which brings us to a really cool modern take on it, a way to visualize building this impossible number.
So this new perspective comes from Vasilescu, who shared his idea back in 2021 on, you guessed it, Pi Day. His approach is totally different. Instead of looking for one single clever construction that gets you close, he asks a new question. What if we could come up with a step-by-step process, an algorithm, to build the number we need decimal place by decimal place for as far as we want to go?
And the starting point is just beautiful in its simplicity. Here's what we do. We take the radius of our circle, and we just decide to call that our unit of measurement. So we say the radius r equals 1. By doing that, the area of our circle, which is pi times r squared, just becomes pi. Simple as that. And if the square has to have an area of pi, then the length of its side has to be the square root of pi. That's our target number, about 1.77245, and so on.
Now, you might be wondering how you'd even do this with just a compass and straightedge. Well, the engine that drives this whole method is actually a classic Greek trick. It's a well-known technique for dividing any line into any number of perfectly equal segments. It's an ancient tool for a modern algorithm.
Okay, so here's how it works. Step by step, it's like building with Legos. First, you start with your radius, which is our length of 1. The first decimal we need is 7. So you use that Greek technique to divide your radius into 10 equal pieces, and you add 7 of them. Boom, you've just constructed a length of 1.7. Now for the next decimal, another 7. You take just that last little segment you added, that 7th tenth, and you divide it into 10 tiny pieces and add 7 of those. Now your line is 1.77 long. You see the pattern? You just keep repeating the process, zooming in on the last piece and adding the next decimal. You can do this forever for any known decimal of the square root of pi.
So what's the big deal? How is this different from, say, Ramanujan's brilliant approximation? Well, think of it this way. Ramanujan's method gives you one single static construction. It's like a photograph, a beautiful, incredibly accurate snapshot. Vasilescu's method is different. It's not a snapshot, it's a recipe. It's an algorithm that gives you a repeatable process to get as close as you could ever want. It's the whole movie, not just a single frame.
This kind of recursive approach is just a perfect blend of the old and the new. You're using the ancient classical tools of the Greeks to run a very modern algorithmic process. Now, let's be clear, this doesn't solve the impossible problem. It can't. But what it does do is give us this powerful step-by-step way to construct an approximation to literally any degree of accuracy you can imagine.
And that really brings us to the big takeaway here. If a problem is proven to be impossible, does that mean we should just stop thinking about it? The quest to square the circle shows us that the answer is a definite no. The chase led to a much deeper understanding of numbers, it forced us to invent whole new areas of math, and even today, it's still inspiring new ways to think about these ancient challenges. It just goes to show you that sometimes the most valuable thing isn't finding the answer, but everything you discover along the way.